This video is on section 5.5 notes, the inverse trig functions. So first, I want you to recall some things that you've learned in the past about inverse functions in general. So first we have inverse operations, are operations that undo each other. Addition and subtraction, multiplication and division, squaring something and square rooting something, exponents and logarithms. So those are things that you've learned about already. An inverse function is a function that serves to undo another function. And when we look at the graphs of inverse functions, we'll see that if you have the line y equals x graphed, I'm going to draw just a little sketch of it. Y equals x is a straight line that has a y-intercept of 0 and a slope of 1. Goes up 1 over 1, up 1 over 1. So it looks like this. If you were to graph a function and its inverse, they would be perfectly symmetrical over that line. They would be mirrored over that line. Another thing we know about functions and their inverses is that if the function has the point xy, then the inverse has the point yx. That means whatever point the function has, you just have to flip the coordinates, and that's what the inverse would have. And then last, in order for functions to be invertible, they have to pass the horizontal line test. If they don't pass the horizontal line test, then it means that when you take them and find all the inverse operations, the equation you end up with is no longer a function. So for a function to be something you can get the inverse of, it has to pass the horizontal line test. Okay, so the first inverse trig function we're going to talk about is sine inverse. So first, this is the original function. The original function is usually written as f of x or y equals sine, and then they use alpha or theta or something. So they use sine of whatever the variable is, and what they're talking about is you're plugging in an angle, and your output is some ratio that represents the opposite side of a right triangle over the hypotenuse of a right triangle. So you have a function is sine of an angle equals a ratio. That's what you have. So if we do the inverse, then we're going to do our inverse operation on both sides. And sine inverse is going to undo sine. And so when we write our inverse function, what we end up with is sine inverse of the ratio is equal to an angle. So in trigonometry, the inverse allows you to find the angle measurement when you know the trig ratio. Okay, so before, when we were dealing with the function, it was backwards. If you knew the angle, then you could get to the trig ratio. Now we're going to start with the trig ratio, and we're going to go backwards, and we're going to get to the angle. Okay, so we're going to look at this visually with some graphs. When we talk about the sine graph, and we look at this, we can see that the sine graph has a range from -1 to +1, and its domain is -infinity to +infinity, and there is no way that this periodic function that repeats this curve over and over and over again is going to pass the horizontal line test. So we have to do something to make it so we're allowed to have an inverse. So one thing we can do is we can cut down the domain and use less of the function. So that's what I've done from here to here, is I cut down the domain a little bit. But here, this is still not going to pass the horizontal line test. This is still not invertible. So what I did is I took this and I cut down the domain even more. And if you cut it down even more, you can cut it to right here. And if you bring the domain from -infinity to +infinity and cut it so it's from -π/2 to +π/2, you end up with a piece of the sine curve that you can find the inverse of. So this right here is a piece of the sine curve that is invertible. And this piece, this is the function, this piece has a domain of -π/2 to +π/2, and it still has a radius, not a radius, sorry, range. It still has a range of -1 to +1. So if we switch from this now to seeing a graph of the inverse, the blue is the sine curve, the pink is the inverse. And you can see it, we've got it reflected over the line y equals x. So the original function had a domain of negative pi halves to positive pi halves in a range of -1 to +1. The domain describes the x's, the range describes the y's. Well, when we get an inverse, we invert those two. So what used to describe the y's now describes the x's. So if I look at the pink function, I can look at what describes the x's now, and the x values are between -1 and 1. And unfortunately, the graph that I used would not let me change these values. I had to keep them in terms of pi. But from here to here, these values are from -1 to +1 on the pink graph. My new range values, or my outputs, are now in between. On the pink graph, my outputs are between negative pi halves and positive pi halves. So in my inverse function for sine, the x coordinates represent my ratios. These are my ratio inputs. And the y coordinates, or the range, represent my angle outputs. Okay, so this is what the sine inverse curve looks like. Now, how does that help us? If we are going and doing some problems where they tell us to find sine inverse of something, find the exact value of the expression, and they're asking us to do sine inverse. Arcsine is just another way of saying sine inverse. Some textbooks use different expressions. If they're telling us to do that, we know, based on this graph, that the answer has to be between negative pi halves and positive pi halves. That's the only piece of the graph we have for sine inverse. So if I'm trying to evaluate these trig ratios and figure out what angle it is, the angle is going to have to be between negative pi halves and positive pi halves. So I'm going to write these in down here because a lot of students don't think of this as negative pi halves, and this is negative pi thirds, and this is negative pi fourths. But when we deal with inverses, we have to think of it that way because that is the domain of the inverse function. So this is negative pi halves. This is down pi thirds, so this is negative pi thirds. This is down pi fourths, so that's negative pi fourths. This is down pi sixths, so that's negative pi sixths. Okay, so what we're doing now is we're saying I'm looking for sine somewhere in between negative pi halves and positive pi halves, so somewhere in quadrant 1 or 4. I'm looking for sine to be 1/2. I'm looking for a y coordinate of 1/2. The y coordinate of 1/2 is right here. That's at pi 6. So my angle is pi over 6. Sine inverse, I'm looking for my y coordinate to be negative √3/2. Here, negative pi thirds. All right, next one, I'm looking for my y coordinate to be √2/2, right there, pi fourths. Sine inverse, I'm looking for my y coordinate to be -1, right here, negative pi halves. Okay, if I'm doing a calculator problem, they're going to say find the calculator angle somewhere between either negative pi halves and pi halves if they're talking about a radian measurement, or somewhere between negative 90 degrees and positive 90 degrees if they're talking about a degree measurement. So here they said sine of some angle equals this ratio, and to solve for that angle we're going to have to do sine inverse. So sine inverse, sine inverse. So alpha is sine inverse of 0.88. Since they want the answer in degrees, I have to take the mode and make sure I'm in degrees, which I happen to be right now. So sine inverse is in blue above the sine button. And so I'm going to do second sine, and I'm going to type 0.88, 61.6. Next one, get alpha by doing sine inverse. Sine inverse, negative 0.27. Okay. Now they want me to do the same thing again with the exact same ratios, but they want me to have my answer in radians instead of degrees. So I'm going to hit the mode button, convert into radians, and I don't even have to type it again. I can just highlight this, the radians, and they're saying to the nearest thousandth, that's 3 decimal places. So 1.076. And then negative 0.27, negative 0.273. All right. We're going to go through the process again, but we're going to look at cos. So here, if we want to find the inverse function for cos, we just have to do cos inverse of each side. And so the inverse function for cos is going to say cos inverse of the adjacent side divided by the hypotenuse is going to give us the angle. And so just like we talked about with sine, if we use the entire cosine curve, it's not invertible. We have to narrow it down. And so if I start to limit the domain a little bit, I still can't use this. This is still not invertible because it does not pass the horizontal line test. I have to narrow it down even more. And if I cut it down this far, I end up with a piece of the curve I can use because it passes the horizontal line test. So I'm going to take the original function, the original cosine curve, and I'm going to limit the domain to 0 and pi. If I make the domain from 0 on the left to pi on the right, then it will pass the horizontal line test. So for my original cosine function, I'm going to say my domain is from 0 to pi. The range is still from -1 to +1. All right, now when I go over here and I keep 0 to pi, there's my cosine graph, and I draw in my line y equals x. Now my cos inverse graph is the reflection of that. So you can see the pink one. And so we'll notice that for our inverse cos function, that domain of 0 to pi has become the range. The range is now from 0 to pi. The original range that was -1 to 1, we see an output of -1 to 1, became an input from -1 to 1. It's written in terms of radians, but it's from left to right, it's from -1 to 1. So the domain here is -1 to 1, and those are the ratio inputs. And then our range is from 0 to pi, and those are the angle outputs. So if we are going to take this information and think about using it to solve some problems, that means that when we look on the unit circle to solve some problems, we're going to have angle outputs that are between 0 and pi. And the angle outputs that are between 0 and pi are up here in quadrants 1 and 2. So that's where we're going to look for cos inverse. So sine inverse, we looked in quadrants 1 and 4. We looked at 1 and 4, and we had to look at negative angles right here because that's what the graph told us. It told us we could only have values for the angle measurement that were between negative pi halves and positive pi halves. That was the only way it would work for us to take the inverse. For cos, the only way for it to work for us to take the inverse is if we use angle measurements between 0 and pi. And so that's going to give us answers that are from quadrants 1 and 2. So cos inverse, we're looking for the ratio root 3 over 2, and we're looking for that as an x-coordinate. So root 3 over 2 is an x-coordinate right here, and so that is pi over 6. Cos inverse of 1/2. The x-coordinate is right here. That's pi over 3. Cos inverse of negative root 2 over 2. That's right here. That's 3 pi fourths. Cos inverse or arc cos of negative 1. Negative 1, that's pi. All right, so here if we're using a calculator, same thing or similar idea to sine, we can only have outputs that are between 0 and 180 degrees or between 0 and pi. So up here, I'm going to solve for alpha by doing cos inverse of each side. And so alpha is cos inverse of 0.23. And I'm going to convert my calculator into degrees. I'll change the mode so that I'm in degrees. So cos inverse of 0.23, 76.7. And then cos inverse of negative 0.82. 145.1 degrees. And then I'll go ahead and find the radian measurements by changing this back into radians. And we'll do both of these again. 1.339. 2.532. Okay, at this point you know the drill. We're going to find tangent inverse. And so the inverse function for tangent is tangent inverse of opposite over adjacent is equal to the angle. And so if we look at all of the tangent function, it's not going to pass the horizontal line test. That's going to be an issue. And so I started to narrow it down and look at a more limited domain. And if I limit tangent, so I'm only looking at one of the curves, not all of them, just one of them, then this one curve is invertible. And so to look at just one curve at a time, I limited the domain to be between negative pi halves and positive pi halves. That would give me one curve of the tangent function. And so for my function, I have a domain of negative pi halves to positive pi halves. And here this is a little bit different from sine because with sine we included the pi halves in part of our answers. We had brackets around here. This time I don't because the pi halves are asymptotes. So I'm not including them. And then for my range, this graph goes up and down forever. And so my range is negative infinity to infinity. Now, when I graph the tangent function with its inverse, this limited piece of the tangent function with its inverse, you can see if you compare it to your notes for sine and sine inverse, it looks very similar. The only difference is these ends go forever, and these ends go forever. They don't just stop suddenly. So here's the line y equals x. We've got the tangent curve, one piece of the tangent curve, and here's tangent inverse. And so we're going to say for our inverse function, the domain is from negative infinity to infinity. This pink curve goes forever, and it has horizontal asymptotes at negative pi halves and positive pi halves. Okay, and I'm going to write that. We have horizontal asymptotes at y equals negative pi halves, y equals positive pi halves. Okay, because we used to have vertical asymptotes at x equals negative pi halves and x equals positive pi halves. So now those have become horizontal asymptotes. And then what used to be the range, or what used to be the domain, is now the range. Negative pi halves to pi halves. So the domain, the inputs, those are the ratios, and they are not stuck between -1 and 1 because it's opposite over adjacent, and so we don't have any limitation to how big those two sides are in comparison to one another. When you talk about opposite over hypotenuse and adjacent over hypotenuse, when you talk about sine and cosine, that ratio always has to be less than 1. Because you always have a smaller side over a bigger side. But with opposite and adjacent, those two sides are interchangeable. Either one of them could be the smallest or the biggest. So the domain, those ratios can be any sort of value that you want. So here's our ratios. And then our outputs is where our angles are going to come from. And you probably guessed it already, but if our outputs, if our angles are between negative pi halves and positive pi halves, then this is just like sine, and we're talking about quadrants 1 and 4 again. So if I'm looking at my next page of notes, and I'm trying to find tangent inverse, I'm going to have to look at quadrants 1 and 4. Now, what I'm going to have to be careful of, and what I'm going to have to be aware of when I do these problems, is that tangent inverse is using a ratio of two different coordinates that we see on our paper, and they have done the work already. So we know that tangent is y divided by x, and so this is tangent inverse of y divided by x, and they probably didn't write root 3 over 2 divided by 1 over 2. They probably simplified it. So this isn't literally tan inverse of 0. I'm not looking for a 0 coordinate somewhere. I'm looking for a ratio y divided by x that simplified to become 0. I'm looking for a ratio y divided by x that simplified to become root 3. I'm looking for a ratio that simplified to become root 3 over 3. I'm looking for a ratio that simplified to become 1. So that's what you have to be careful of with tan, is that you don't actually see it written on your unit circle. So for tangent, 0 would have come from one of these. It's not 1 divided by 0, that's undefined. It's from 0 divided by 1. So this is actually 0 divided by 1, and tan inverse of 0 divided by 1 is just 0. Okay, root 3 would come from one of the angles that has a root 3 in it. So it's not going to come from down here, because then it would have been negative. You would have had a negative y coordinate divided by a positive x coordinate, and you would have ended up with a negative. So we're definitely dealing with one of the ones up here. If we think about y divided by x, for this one, we would have had 1/2 divided by root 3 over 2. We know that the 2's cancel, so we would have had 1 over root 3, and we would have had to fix it. So that's not the one that it is. For this one, we would have had root 3 over 2 divided by 1 over 2, and the 2's would have canceled, and we would have had root 3 over 1. So this is it. So this is root 3 over 2 divided by 1 over 2. That's what became root 3. And so that is pi thirds. Okay? Negative root 3 over 3. So now we have a negative, which means we're looking at these ones down here. Again, we have these two options, and since it was negative root 3 over 3, we're looking at this one. We must have had negative 1 over 2 divided by root 3 over 2. The 2's canceled, and negative 1 over root 3 had to be fixed because it had a root in the denominator. So it's this one. This was negative 1/2 over root 3 over 2. And so that is negative pi over 6. Okay? And then for negative 1, this one's kind of tricky. For y divided by x to become a 1, you had to have the same fraction divided by itself. So it's this one right here or this one right here. And it's a negative 1. So it must be this one. So this was negative root 2 over 2 divided by root 2 over 2. And that makes it negative pi over 4. Okay, so let's go ahead and use our calculator. Again, they're having us do degrees and radians, and they're telling us to look for answers that are in the 4th quadrant and 1st quadrant. And so to solve for alpha, we're going to take tan inverse. And first I need to be in degrees. So tan inverse of 1.45 is 55.4 degrees. And then tan inverse of negative 3.87 is negative 75.5 degrees. And then we want those same measurements, but in radians. 0.967. Negative 1.318. All right, this here is a summary. So what this summarizes is when you're doing these problems and you're using the unit circle because they told you to write an exact value for your angle measurement. This is where you can look on the unit circle when you're using inverse trig functions. If you have sine or tangent inverse, you have to look in quadrants 1 and 4. If you're looking for cos inverse, you can use quadrants 1 and 2. And then we should add some extra information here that we're going to do negative pi halves, negative pi thirds, negative pi fourths, negative pi sixths, that if we use quadrant 4, we have to have the negative version of the angles because the domain for our inverse functions was negative pi halves to positive pi halves. So when we use quadrant 4 to look for those answers, we have to use the negative version of the angles to do that. Now that we've talked about the inverse trig functions that we're going to use most often, sine inverse, cos inverse, tan inverse, we're still going to talk about the other 3 inverse trig functions and make sure that we can work with those as well. So we have cosecant of an angle is hypotenuse over opposite. That means to get the angle alone, we have to do cosecant inverse of both sides, and we get that the angle is cosecant inverse of hypotenuse over opposite. So notice this is very similar to cos. The angle would be, not cos, sine. This is very similar to sine. The angle would be sine inverse of opposite over hypotenuse. So again, we're still talking about reciprocals when we deal with these other trig functions. For this one, we know that the angle would be secant inverse of hypotenuse over adjacent. And for cotangent, the angle would be cotangent inverse of adjacent over opposite. And sometimes it will actually be more helpful to think of this as cotangent inverse of x divided by y. So we'll also look at that. Now, before we move on to the next section and actually doing some practice with these, we're going to talk about which quadrants you look for answers in. And I'm not going to go back and show you the graphs like I did with sine inverse, cos inverse, and tan inverse. But if you are curious to know, we can talk about it. You can ask me, and then I can walk you through how the graphs of these functions can be reflected over the line y equals x to help us figure out what quadrants to look in. So there's two that are kind of intuitive and one that feels kind of weird. So with cos inverse, if you take the reciprocal and we do secant inverse, we look in the same quadrants as cos. So I'm going to write secant inverse here of x and secant inverse here. So we're going to look in quadrants 1 and 2. Sine and cosecant are reciprocals of each other, so these are also a little bit intuitive. Sine, you look in quadrant 1 and 4, and when you get a quadrant 4 answer, you write the negative angle measurement. Same thing is true for cosecant. So cosecant inverse of x, cosecant inverse of x. The one that is not as intuitive is that cotangent does not use 1 and 4 as the reciprocal of tangent. It actually comes from quadrants 1 and 2 if we use cotangent inverse. So for any of those three, if you want to see why they work in those quadrants, feel free to shoot me an email or ask me after class and we can talk about it. All right, so we're going to go ahead and find the exact value of some of these inverse trig expressions. And these ones, since they say exact value, that means I'm using my unit circle. So arc secant is the same thing as secant inverse, if you're more comfortable looking at it that way. And this is the reciprocal of cos. So what I can really think of is the reciprocal of -2, which would be -1/2, and I would be asking myself where on the unit circle is there an x coordinate that's -1/2, and specifically I'm looking at quadrants 1 and 2. So for secant inverse, I can look at quadrants 1 and 2. So quadrant 1 and 2, I'm looking for a -1/2, that's right here, and so my answer would be 2π3. Cosecant inverse of √2, that means I would be looking for sine inverse of 1 over √2. And this is not what is going to show up on the unit circle. The unit circle has rationalized fractions, and so I can go ahead and do a little bit of math here to see what would actually show up on the unit circle. I can rationalize the denominator. I get √2 over 2. So sine inverse or cosecant inverse tells me to look in quadrants 1 and 4, and in quadrants 1 and 4 I am looking for a y coordinate that is √2 over 2. So that's going to be in quadrant 1 because we're going up to a y coordinate of √2 over 2. π4 is my answer. Okay. For cotangent inverse, I don't really need to think of this as tangent inverse. I don't need to think of it as the reciprocal. I can just recognize that cotangent inverse is an x value divided by a y value. And somehow I had to have an x value divided by a y value that simplifies to become √3 over 3. So if you're starting to recognize these, you might recognize that that would be 1/2 divided by √3 over 2. And it would have to be simplified to become negative √3 over 3. We also know somewhere in here we're going to have a negative sign. So with cotangent inverse, I am not doing this like tangent inverse. I'm not looking at quadrant 1 and 4. For cotangent inverse, I'm actually looking at quadrant 1 and 2. So I'm looking for x and y coordinates, where the x coordinate is 1/2, the y coordinate is √3 over 2, and somewhere there's a negative sign in quadrant 1 and 2. So x coordinate is 1/2, y coordinate is √3 over 2. Somewhere in there there's a negative, it's with the x coordinate, and so this is 2π3. Okay, and then last over here we have arc cosecant. So this is cosecant inverse to √3 over 3. And so I'm going to be looking for sine inverse 3 over 2 root 3. And again, just like before with sine, this is not what we would find on the unit circle. The value that we're going to find on the unit circle is going to have a denominator that has been rationalized. So I'm going to go ahead and do that math. If you have done enough of these problems, you might already recognize what fraction gave you this, or you might be able to just kind of use your intuition. But if I was to rationalize this, I would multiply the top by root 3 and the bottom by root 3. 3 root 3 on the top. On the bottom, I have a 2 multiplied by root 3 times root 3. Root 3 times root 3 is root 9, which is just 3. So I have 2 times 3 on the bottom, which is 6. And then over here, I can take the 3 over 6 and I can reduce it to get 1/2. So I have root 3 on the top and 1 and then 2 on the bottom, root 3 over 2, which makes sense. So let's go ahead, and for sine, we're going to look in quadrants 1 and 4, and we're looking for a positive root 3 over 2. So y coordinate positive root 3 over 2, and quadrant 1 is pi thirds. All right, now we're going to go ahead and turn to the next page, which is going to lead us to some calculator problems. So here we have arc cosecant. So we don't have a cosecant button, which means we can't do arc cosecant. So for us to be able to plug this into the calculator, that means we have to use sine and arc sine to plug it in. So I'm going to write that this is sine inverse of 1 over 2.4. So 2.4, if I was to write it as a fraction, I could just say 2.4 over 1. And so that makes this the reciprocal. And so now, whenever I do these problems, remember that this is a ratio. It's a ratio of two sides of a triangle, and the answer that I'm getting is an angle. Unless they specify that they want your angle to be in degrees, you should automatically just assume it's in radians, because that's what we typically work with in this course. And so I'm just going to double check that my mode is in radians. And now I can do sine inverse. So second sine, 1 divided by 2.4. And it says to round to 4 decimal places. So I have 0.4298. Here, cosecant inverse of -4, I'm going to do sine inverse -1/4, or 1 divided by -4. -0.2527. Secant inverse of 1 is the same as cos inverse of 1, actually, because 1 written as a fraction is just 1 over 1. So when I find the reciprocal, I'm still just going to have 1. So cos inverse of 1 is 0. And then arc secant, so we're going to do cos inverse of the reciprocal, 1 divided by -3.62. .8507. All right. The next few examples are compositions of functions. You have one function on the inside, one function on the outside. Sometimes we have an inverse function on the inside and a regular function on the outside. Sometimes it's vice versa. And so we're just going to go through and do each of these, and you always work with the inside first. So first, I'm going to look for tan inverse. That means I'm using quadrants 1 and 4 of 0. So I'm looking for a fraction where the y-coordinate divided by the x-coordinate is 0. And I can see that happens right here at 0 radians. So I have sine of 0 radians. And so now I'm going to look at 0 radians. Sine of 0 radians is the y-coordinate, and so the answer is 0. Arc sine of cos of pi 6. So the first thing I'm going to do is look for pi 6 and find cos, which would be the x-coordinate, root 3 over 2. So that means that I'm finding sine inverse, or arc sine, of root 3 over 2. And then for sine, I know that I need to look in quadrants 1 and 4, and I'm looking for what angle in quadrants 1 and 4 have a y coordinate of root 3 over 2. So these two, a y coordinate of root 3 over 2 is pi thirds. Tan of secant inverse of root 2, so this is going to be tan of cos inverse of 1 over root 2. And I think we did this on the notes already. We did. Not this exact problem, but we worked with this fraction. So we said this fraction does not show up on the unit circle. You have to rationalize the denominator. And when you rationalize the denominator, you get root 2 over 2. So this is tan of cos inverse of root 2 over 2. So for cos inverse, we look in quadrants 1 and 2. We're looking for an x coordinate of root 2 over 2, which is right here at pi fourths. So that means we are doing tan of pi fourths. Tan of pi fourths is the y coordinate divided by the x coordinate. The y coordinate's root 2 over 2. The x coordinate is root 2 over 2, and those are the same. And so I'm going to go ahead and just kind of show some work here. Y coordinate divided by the x coordinate, they're the same, so that gives me 1. Tan of pi fourths is 1. All right. The last problem says, why isn't arcsine of sine of 4 pi thirds, why doesn't that equal 4 pi thirds? So arcsine is sine inverse, and we have learned in the past that inverses undo each other. Plus and minus are inverses, they undo each other. Add and subtract are inverses, they undo each other. Square and square rooting are inverses that undo each other. Logs and exponential functions are inverses that undo each other. But here they're saying arcsine or sine inverse and sine that they don't cancel out and give you 4 pi thirds is 4 pi thirds. And the question is why? The answer has to do with where your answers can be for arcsine or for sine inverse. So we're going to do this problem and then we're going to explain why it doesn't work. So we're going to start with the inside, sine of 4 pi thirds. And sine of 4 pi thirds is over here. It's the y coordinate negative root 3 over 2. So we are finding sine inverse or arcsine of negative root 3 over 2. And then we're going to evaluate what this is. So for sine inverse, we use quadrants 1 and 4. And we're looking for a y coordinate of negative root 3 over 2. That's down here. And we have to count, we have to do negative angles. So negative pi 6, negative pi fourths, negative pi thirds. And so the answer is actually negative pi thirds. So the reason that this doesn't work is because this output of 4 pi thirds is not in the range, it's not in the list of all possible outputs of sine inverse functions. So this output, 4 pi thirds, is not in the range of sine inverse. So if 4 pi thirds is not a possible output, it's not within the range of outputs, then you're not going to be able to cancel those and get that answer. So that's kind of a little trick specifically about these inverse functions. The takeaway message for you is that if you're evaluating this, don't make them cancel, do the steps, show your work, and make sure that you get the correct answer.